At 24,000 feet, the roof of a Boeing 737 tore away. The cabin was suddenly open to the sky. The airplane kept flying. This was Aloha Airlines Flight 243, traveling from Hilo to Honolulu on April 28, 1988. About 18 feet of the upper fuselage separated just behind the cockpit. A flight attendant was swept overboard. 94 other people remained inside a damaged pressure vessel moving hundreds of miles per hour. The failure looked instantaneous. It had actually been developing, one flight at a time, for years. The aircraft was nearly 20 years old, but age in years was not the most important number. Its daily work consisted of short inter-island flights. Every climb pressurized the cabin. Every descent released that pressure. One trip created one more load cycle in the fuselage skin. By the accident, the airplane had accumulated 89,680 flight cycles, but only 35,496 flight hours. The cycles had accumulated at about twice the rate assumed when the maintenance recommendations were developed. A program based mainly on hours could therefore make a high-cycle aircraft look less used than its structure really was. The critical detail was a lap splice, the longitudinal joint where one aluminum skin panel overlapped another. On early 737s, adhesive bonding was intended to carry the cabin's pressurization load, while rows of rivets held the joint together. But the cold bond process could produce weak or unbonded areas. Moisture entering the joint encouraged corrosion and more disbonding. As the bond degraded, more load shifted into the rivets. Around their countersunk holes, stress became concentrated. Small fatigue cracks began at many neighboring fasteners. Individually, each crack could be difficult to detect and too short to look critical. Together, they changed the problem. They could link across the rivet row and behave like one long crack. A pressurized fuselage is always trying to expand. Its skin carries that outward pull like the wall of a metal cylinder. A sound lap splice spreads the load. A damaged one concentrates it along the weakened seam. As Flight 243 leveled at 24,000 feet, the linked fatigue damage reached a critical state. The joint failed at stringer S10 left. Cabin pressure forced the rupture outward, and the crack ran through a much larger area than the airplane's fail-safe assumptions were expected to allow. The upper crown skin and supporting structure separated. In seconds, a hidden line of tiny defects became an 18-foot opening. The captain took control and began an emergency descent toward Maui. The aircraft was noisy, damaged, and aerodynamically changed, but its wings, engines, and primary flight controls still functioned. The crew brought it onto runway 02 at Kahului. Of the 95 people aboard, one flight attendant, Clarabelle Lansing, was lost. 8 people were seriously injured. Everyone else survived. The successful landing was extraordinary, but it did not make the structural failure less severe. Investigators had to explain how a design intended to tolerate damage had allowed so many cracks to grow together before the danger was recognized. The investigation found a chain, not a single bad part. A joint vulnerable to disbonding and corrosion, repeated pressure cycles, cracks forming at adjacent rivet holes, inspections and maintenance that did not reveal the full condition, and rules that required attention to only part of the lap splice problem. The accident accelerated work on aging aircraft structures, widespread fatigue damage, better non-destructive inspection, full-scale fatigue testing, and maintenance limits tied to how aircraft are actually used. Its lesson is simple enough to carry beyond aviation. We often look for the largest visible defect, but a system can lose its safety margin through many small defects that interact. Small cracks do not stay small when the load gives them a path to join.